Lei aveva... Secondo me non aveva l'audio. Secondo me non aveva l'audio on. Perché il messaggio gli era arrivato.
Can anybody hear us from the remote connection?
Yes.
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 No. Can you hear us?
Mi sa di no.
It's green.
Però qua mi dice, cioè, qui lo prende l'audio.
Ah, ok, hanno detto sì.
Ah, top, ok.
Okay, so I think we can slowly start. Okay, so it's a pleasure to have Matilde back in Bologna after a few years.
Yes.
So Matilde got her master here in Bologna and then also did PhD working both here in Bologna and she was based at INA Parcetri. She's an expert in ISM modeling and observations. She will tell us more during the presentation. And now she is a staff astronomer at Space Telescope in Baltimore, where she has a position jointly funded by ESA and NASA. Okay. So, and today she will talk about an infrared to UV view of a nearby high redshift analog with JWST and HST to interpret the first galaxies.
Thank you very much, Cynthia. Thank you very much also for inviting me today. It's always a pleasure to be back in Bologna. Yeah, as Liva was saying, I have this position at Space Telescope that is a ESA or a position. So basically for 50% of my time, I support STS on HST. And that is one of the instruments, the oldest instrument alive on HST. And the other 50% of my time, I do research. And today I will present some of the last results that we have obtained in my group. And I want to say that I work in collaboration with many people. Some of them highlighted here, and I specifically want to highlight the contribution of two early career researchers, two postdocs in our group that are Macarena Garcia del Valle and Ryan Rickardsvold, who really did a lot of work for the things that I will present today. I want to start from like from this cartoon of the cosmic timeline that shows the different epochs of the history of our universe. And this is the most recent version, I think. It's really beautiful. And there are still, of course, many open questions and related to the galaxy evolution. And they all start from the first stars and galaxies that reionized our universe. Now with JWST, we have precious spectra for the first time of objects up to redshift 14.4, I think. This was true till a few weeks ago. I think it's still true. And of course, this is another high redshift galaxy, a very famous one, GNZ11 at redshift 10.6. And with JWST, these are near spec data, we can see for the first time spectra for these objects, and in particular the rest frame UV of these very far galaxies. Of course, this is incredible with respect to what we could do before, but at the same time, we have still a limited view. Like we have a limited view of these very distant systems, and it can be difficult to use the emission lines available in the rest frame UV, and for a galaxy at redshift 10.6, we start to see the blue part of the optical to interpret the properties of these systems. That is why we think that it's still very important to use the nearby universe, the local universe, and in particular galaxies that are considered analogs to these redshift systems. And to be considered analog, it means that they are metal poor, they have a low mass, they are compact, they have a starburst activity. This is an example. This is one UV spectrum of one of these blue compact dwarfs. And so using these objects, it can be a good tool to understand what is going on in these conditions and then use these to interpret the redshift universe. So this is the idea behind this kind of research. And I started to do this work in particular when I moved to Space Telescope in 2020 as a postdoc, and I joined the CLASSI collaboration. CLASSI is a Treasury HST program, cycle 27. The PI is Daniel Berg, and it's a survey of 45 local star-forming galaxies with the full res frame far UV spectral coverage. So this is an example in purple of the spectrum that you can get with HST COS, very high spectral resolution. And you can study all the UV features that you can see here. So the absorption lines, the emission lines, and you can really characterize these systems. This was one of the aim of the CLASSI survey. And these galaxies were selected to be to have similar conditions of the high-redshift universe in terms of star formation, stellar mass, gas phase metallicity, etc. For example, here on the left, you can see the star formation rate versus stellar mass. The CLASSI galaxies are located here, are the purple points, and are more consistent with high redshift data than with the local relations that he studies over here. So my role within the CLASSI collaboration was to study the ISM properties of these systems using the optical, the UV and the optical that we had from ground-based observatories, and to see if it was possible to create a UV-based toolkit to measure the gas properties and apply these for the high redshift galaxies. So these are like some of the results of the CLASSI survey that we obtained. We studied, for example, different diagnostics to infer the gas density from the UV and we compare them to the optical, finding that in general, like UV gas tracers tend to find higher densities, and so we need to take that into account when we study the high redshift universe using UV tracers. We explored different diagnostic diagrams also to infer the source of ionization, so basically the UV version of the BPT diagrams and so on. I want to go back and of course, this is just a part of what we have done with CLASSI. There are a lot of other results, including Lyman alpha studies, etc. And I think that now the CLASSI results are starting to give good information to interpret the high redshift universe. But I want to go back to what I was saying before, because the local universe is not only important for the res frame UV. If we are in the local universe, we can have a multi-wavelength coverage of objects of these high redshift analogs, because apart from the UV, we can get the optical, of course, with ground-based observatories. We can get now the infrared with JWST. This is, for example, the MIRI, the mid-infrared spectrum of the same target, and indeed, the CLASSI project will be expanded, because in cycle 4, Daniel Berg and Bethan James, they both PI the CLASSI year. And so we will have the extension in the UV, in the mid-infrared of the CLASSI survey. In general, this is a great way to exploit all the multi-wavelength information that we can have in the local universe to interpret the redshift universe. And of course, apart from this, we can have also radio observations and sub-millimeter and so on. But the talk today, I want to focus specifically on one galaxy, that is the galaxy I was showing you in the spectra before, that is SBS 0335-052e. I am saying here that is the perfect local high redshift analog. Of course, it's not perfect, but it's really a good example, because it's an extremely metal poor galaxy. Extremely metal poor means 5% solar. With a compact, vigorous starburst. You can see here, this is a UV image of this galaxy, and you can see in dark in black here, the different stellar clusters that have been studied in multiple papers during the years, because this is a very famous local objects. These are all superstellar clusters, plus there are some regions of recent star formation that are more visible in H alpha, and the black contours here are the H alpha contours. There is also a ULX over, like in this dense starburst region, this galaxy is also well known to have high ionization UV and optical emission lines. It was proposed to host an intermediate massive black hole because it shows neon 5 emission in the optical that was actually discovered in 2005 by Thuan and Isotov, but the idea that it could host an intermediate massive black hole was proposed by Atano 2024. And it has also a broad H-alpha profile that now is a very common feature that we see at high redshift. So there are really a lot of elements that make these the perfect high redshift analog. In my JWST cycle 2 program, I targeted this object and other 5 nearby redshift analogs. The aim was to study the conditions of the warm molecular gas, and I hope there will be a little bit of time at the end of the talk to show you some preliminary results about that. But here I want to focus on another work that we have started as soon as we looked at the data for the first time, because when we looked at the data of SBS, the first thing that we saw was an incredible point source. You can see here, this is an image in channel 3 that covers from 12 to 17 micron, but you can see these point source emission basically all over the mid-infrared of this object. And yeah, you can see the point source over here. And of course, the first thing that we needed to do was to model the point source contribution and subtract it, because our aim was to study what was underlying the point source emission. The point source is actually located more or less over here, where there is the superstellar cluster 1. And previous NICMOS data, so infrared data with HST, actually showed multiple point sources in this galaxy. And this is probably because there are a lot of compact subforming regions which are causing the point source emission in the JWST data. So we modeled the point source emission. This is the spectrum that we recovered. You can see a clear feature, like a clear interesting feature is the silicate feature, the silicate bump around 10 micron that shows the presence of dust. And indeed, from the study of the mid-infrared continuum, we found a very strong attenuation, like an AV of 15 Mach for this specific region, because the silicate feature is seen in this part of the galaxy and not everywhere else. It's less prominent, let's say, in other regions of the galaxy. And once we subtracted the point source contribution, we could study the extended emission underlying it. Here it's really you can see the MIRI MRS superpower. That is the fact that it covers from 5 micron up to 28 micron, more or less. So you have a lot of emission lines over there. And so you can really study a range of ionization potential, which allow to study the ionization structure of the ISM in practice. So here I'm just showing you some of the emission lines that we see from the sulfur 4 that has an ionization potential similar to oxygen 3, 5007 in the optical, and then neon 3 that is slightly higher, oxygen 4 that starts to be around 55 electron volt, and we also see neon 5. The neon 5 emission at 14.32 micron in particular was never detected in blue compact dwarfs before, probably because of the low sensitivity of Spitzer. There were only upper limits for blue compact dwarfs. Of course, the neon 5 is observed in some of these objects, in particular in this galaxy, using the optical, as I was saying before. But MIRI MRS has the potential for the first time to really spatially resolve the emission and see where this neon 5 is coming from. And in particular, we see that it's coming from this region over here. And that is the region where there are the slightly older stellar clusters. The older means like 15 mega year. It's very young because it's, again, a young starburst system. And the interesting thing is also that it's not coming from the point source, because, I don't know, there is an intermediate massive black hole. Maybe you would think that it's showing like a point source and that the neon 5 is coming from there. But we tried and checked in any way. But the neon 5 is not coming from the point source. The point source doesn't have neon 5. It's all coming from this region over here. Once we have all these, well, the neon 5 has an ionization potential of like 97 electron volts. So it's really difficult to explain only with the star formation, so without an AGN. But we compared like what we did once we had all these maps, we started to study line ratios in order to compare them with models. This is what you do also in the optical with the VPT diagrams. So this is one of the diagnostic diagram that we studied. This is the neon 5, neon 2 versus the neon 3, neon 2 line ratio. These are both tracing while addressing the radiation hardness of the gas, the ionization parameter. Here you can see a map that shows the color coding of this plot, so you can see where the points are coming from. In particular, the points that show the highest neon 5, neon 2, the yellowish here are coming from this region that is just on top of the region where the neon 5 is peaking in the maps I was showing you before. And we compared well, first of all, the neon 5, neon 2 is used as a tracer of AGN. And typically, historically, the star formation AGN separator is over here. So everything that goes above should be an AGN. And all the points of our galaxy are lying in the AGN region. Then we compared the line ratios with with a set of models. We used star formation models, we used X-ray binaries, shocks, and intermediate massive black holes. And in the only grid of models that can be superimposed, at least, that can explain the line ratios that we observe, are the intermediate massive black hole models from Richardson 2022. You see here different grids. These are grids at different AGN fraction. So the grids that can cover better our models are between 4 and 8% of AGN fraction. Last thing I want to say, the point source is this point over here. It's an upper limit because we don't see neon 5 over there. It's still, so this could actually, we are not sure. It could be that it's, we still believe it could be a very young compact stellar cluster. But in the paper, we didn't want to give a final conclusion about the ionization source that is powering this galaxy, because there are still many things that we don't know. In particular, this is the only set of intermediate massive black hole models that are available at the moment. And so we are really model dependent in interpreting our data. So I think that we need to understand better the condition of the gas in these metal pool systems. And for this, it's great that we will have more and more data of other systems similar to SBS. And some of them are showing the neon 5 as well. So we really need to understand what's going on. And also, I'm not sure if we have completely understood how to model massive stars, atmospheres at low metallicity, and also shocks and X-ray binaries. We have not explored probably the entire range of parameters in these metal poor conditions. So it's still probably too early to say, okay, this is an intermediate massive black hole, but still the conclusion at the moment is that the intermediate massive black hole models are the only one that can cover at least the same region of points that we observe. As I was saying at the beginning, this galaxy is part of Classy, and we studied in the UV with the UV line ratios. These are UV line ratios with one cost pointing, so one spectrum, not an IFU. We could study already the ionization source from the UV, and this galaxy is the yellow point over here. That is. In this UV BPT diagram that we did, where we separated star formation, AGN, and shocks, this galaxy was lying in the region that was star forming, but just at the edge. And so we thought that the reason why this galaxy was at the edge is because extremely metal poor galaxies tend to have a higher radiation field, etc. And so they could look similar to an AGN, but they are not. And these were AGN models from Feltre 2016. But actually, I did again this plot for the new paper with the models from Richardson 2022, the intermediate massive black hole models, and clearly the intermediate massive black hole models, especially at low AGN fraction, so with 4-8% of AGN fraction, can go beyond the AGN locus that we claimed, let's say, and they can go in the star formation region. So there are good things and bad things. The good thing is that, I mean, The good thing is that the mid-infrared and UV line ratios can be reproduced by the same set of models for this galaxy, which is interesting. It is mainly, maybe it is telling us that this is actually the good explanation for this system, for SBS. But at the same time are telling us that there is a degeneracy that we didn't know before in this kind of UV diagnostic diagram, in case you have an intermediate massive black hole. So this has to be taken into account to people at high redshift who use these line ratios to determine the main source of ionization. But at the same time, this stays the best UV diagnostic that is capable to separate shocks and AGN at least. But then we need to take into account this unknown degeneracy, let's say. Of course, people at high redshift could say, okay, but we don't see the mid-infrared at high redshift, so why do we care about the mid-infrared coverage of high redshift analogs? It's true that the mid-infrared is not observable at high redshift. We will not observe the NeIII at 14 micron, but the JWST can provide coverage to the NeIII in the optical with NIRSpec. There are actually already some works like Clary 2023 or Chisholm 2024. And this is one of the diagnostic diagrams that these studies explore at high redshift. That is helium-2 H beta, so optical lines, versus NeIII, NeIII, also optical lines. These are like this in blue is one of the galaxies at high redshift, at redshift 6, 5.6. This is from Chisholm 2024. These are some separators that were proposed at high redshift. I think it's from the work of Clary 2023. And these are all blue compact dwarfs similar to SBS that have the NeIII emission in the optical. And so I think that, and here you can see again the intermediate massive black hole models from Richardson that are overplotted here that show that even in the region that is considered star forming, if you have a very low contribution of AGN, you could actually explain this kind of emission. I think that multi-wavelength studies of nearby NeIII emitters of these in these conditions can really help us understand what is going on at high redshift. So this is why we should care despite we don't see the mid-infrared at high redshift. I will be very, very brief because there are many more things that we can do with this data. So this is a very complicated plot, but this is from Berg 2021. It shows how to model star forming regions. This is a 4-zone ionization model that you would need to model star forming regions in metal poor systems, where apart from the classical low, intermediate, and high ionization, you have also a very high ionization region where you have helium-2, for example, and oxygen-4, neon-3, but neon-5, and so on. And the thing that is that with the mid-infrared, we can really have access to this very high ionization region. And in particular, this can be useful also to estimate the true metallicity of objects. This is a work that a postdoc at STScI in our group is doing, Ryan Rickards-Vogt. This paper is submitted to APJ on the Galaxy 1SVK18. These are data from another Cycle 2 program from the PIR Aloisi and Hunt. And Ryan put together KCWI data, so optical IFU with the MIRI MRS, and could estimate the true metallicity of 1SVK18, recreating the gas phase metallicity map, estimating the oxygen abundance, taking into account all the ionization states of oxygen, so oxygen 2, oxygen 3 that you can get from the optical, but also the oxygen 4 from the mid-infrared, and taking into account that when you have the very high or high ionization region, you have to estimate the density with the high ionization region density tracer. And the interesting thing that we find in this work is that this plot is a bit complicated. I will just focus on the part on the right. So in the y-axis there is the oxygen abundance derived using all the states of oxygen 2, oxygen 3, oxygen 4 that is available only from the infrared. And on the x-axis over here, there is the simple version of obtaining the oxygen abundance, so from oxygen 2 and oxygen 3, using only the density of the low ionization region. So from the sulfur 2 lines, for example, in the optical, and clearly you risk of overestimating the metallicity at low metallicity and slightly overestimating it at high metallicity. So it's important basically to use all the emission lines possible to really have a completely full ionization study of the ISM in order to accurately determine the properties like the gas phase metallicity. There are many more things discussed in the paper, and hopefully you will soon be on archive. The last thing I want to mention is that the original aim of the programs, actually both my program and the one from Aloysius and Hunt on these 6 local redshift analogs, including 1SVK18 that is from Aloysius and Hunt, was to study the molecular gas. Because the molecular gas, usually we use CO to determine the molecular gas reservoirs in galaxies. But in metal poor regions, the thing is that because of the harder stellar radiation field and because of the lower content of metallicity, it's more complicated to have CO. And it could be that CO is not a good tracer anymore of the molecular gas. And that is why we wanted to use the H2 rotational transition in the mid-infrared to study, to get the molecular gas content in a different way. This is all work in progress. There is a postdoc that is working with me at Space Telescope, Macarena Garcia del Valle. She has started to look into the H2 transitions, rotational transitions in the galaxies of the MIRI sample. This is the case of SBS. There is still much more to do, and the aim is to really understand we have in the end 5-6 objects. So the idea is to see how the content that we can derive from the warm molecular gas is related to the gas phase metallicity, other ISM properties that we have, and plus we can also use some ALMA data and IRAM data, both from the literature and some data that we got, to have also a view of the molecular gas. So to have really the multi-wavelength view I mentioned at the beginning, and this is all work in preparation. There is also another work on 1SVK18 that is submitted from Leslie Hunt that is very interesting, and so there is a lot really to learn about these systems. And so really stay tuned for the next few months. Hopefully we will have much more to say. Also because from this object, we can also look into the presence or absence of dust features like PAH that at low metallicity are really difficult to find. And maybe there is some tiny evidence somewhere. So really stay tuned. And these are all my conclusions. I probably am over time. So thank you very much for your attention. I hope I convinced you that it's important to have a multi-wavelength view of nearby analogs to understand the edge figures.
So, questions for the speaker?
Yeah, the question regarding the H2. I should know. I have a doubt regarding the modeling of the H2 emission. So if there are hints of the effect of this intermediate black hole having an effect on the ionized gas tracer, would it be possible that they have also some kind of effect on the H2 lines? And so how do you plan to account for this predictive effect?
Yeah, that's a good question. Actually, when we got the data, when we submitted the proposal, we didn't know, like I was convinced that the galaxies were completely start forming because we studied like UV, optical line ratios, etc. And so finding all these extended NeII was kind of surprising. That is why then we focused our first work on that, because it was very interesting. And in the meantime, there was also this work from Atano that was suggesting the presence of the intermediate massive black hole. So definitely this is something we need to look into. Not all the galaxies of the sample are NeII, so definitely it would be interesting maybe to see. And I think that this is something that with Glacier that has 45 galaxies, that will have 45 galaxies with the mid-infrared coverage, I think that from there we will have really a better understanding. What we saw for sure in these galaxies that the the H2, these are really preliminary results and not the great maps, but it's showing that the H2 seems to come from this region over here. That is not the region where we see the neon 5. So it's interesting to see also, like we can do a spatially resolved analysis and try to understand. But yeah, this is all something that we need to, well, we will think about it together, Livia. Yeah.
Do you see evidence of pH in the SBS spectra?
In SBS we tried, but we don't see anything. We tried. I don't know if you would need even deeper data. There is also a MIRI GTO program that has slightly deeper data of this galaxy, so maybe I don't know from that point of view. And definitely in the end, like the galaxy is slightly more extended than what we covered, so maybe there is evidence somewhere else. But in SBS we don't see pH. But there is another galaxy of our system, we are really studying it now, where we see like a tiny evidence of a pH. And it's interesting because it's coming only from a specific region where we see even like a very high ionization. So we're really trying to understand. And it's not the pH you would expect, because I didn't know much about pH till a few weeks ago, and now we see a pH feature that is not the typical one that you would expect, the brightest one. It's around like 11 micron. No, 11 micron can be. So it's tracing like the neutral dust in that sense. And we are trying to understand what is going on. But that is the only evidence, and it's a very tiny evidence. So really, you need a lot of like deep data, probably.
It's also a galaxy.
It's also not like SBS. It's slightly more metal rich, but still below 20%. So like below, it's around 15% solar, 10% solar. It has an oxygen abundance of 7.8. But also there is a slight variation of metallicity. But yeah, no, as metal poor as SBS, we don't see pH at the moment.
Do you have the X-ray or radio data for the source?
So radio data, so X-ray, yes. SBS in particular was studied in the X-rays. There is a work from, now I don't remember the name, but there is this work that compared the X-ray data and the helium-2 emission in the optical. Helium-2 has, again, an ionization potential of 55 electron volt, so very high ionization. And in that work, it was Carrig 2018. I can show you later. In that work, they compared the X-ray emission that is coming from this ULX that is located over here. There is this ULX that, according to the Chandra data, is over there. And they claim in that study that the X-ray coming from this ULX is not enough to ionize the helium-2. And so so if it can't ionize the helium-2, it's unlikely that can ionize something that is even more ionized. And the other galaxies, I'm not sure, but definitely there is something. Sometimes there are ULX observed in these, like in 1SVK18, there is also evidence of a ULX, but nothing crazy, like not. And the radio, I think there are H1 studies, and I think there was a work in preparation on the radio data, but I'm not sure at which stage is that.
Maybe I missed it, but this the galaxy would be the black hole to stellar switch. Does it lie on the establishment of variations, or is it an outlier?
So this galaxy, now I don't remember, I think it's around 10 to the 7. I need to check. I forgot. I should have checked before. It's a small compact galaxy, and the models. I mean, I think that this is not the perfect way to estimate the mass of the black hole. So what we did is that we used different grids of models, and the models with the mass 10 to the 5 were reproducing in a good way the data. If you use black hole masses that have slightly lower mass, like 10 to the 3, 10 to the 4, you, like, all the line ratios are shifted to the left, and you cannot reproduce anymore the neon 3, neon 2. So that is why we use the 10 to the 5. But there are a lot of parameters in the models that can be degenerate. I think the black hole mass is degenerate with the ionization, like the spectrum, the ionization in the spectrum, and there are other factors to take into account. So this is not the best way to say, okay, there is a 10 to the 5. If it was 10 to the 5 stellar mass, the black hole, then it would be slightly above the typical relation. So it would be similar to what like Roberto Maiolino and other people at iRedshift are finding.
If there are no more questions, then we can speak again. And we still have one last talk next Tuesday.
Thank you very much.
Thank you.
Thank you so much.